Uh, I'm going to share a few thoughts on machine learning, more, a little bit on deep learning. Anyway, this is more like an overview talk, so I won't do too much of detail on anything, but you have, I believe, detailed lectures on each topic in the days to come. Next slide. This is first of all acknowledgement. Many of the slides are contributed by my PhD students and some are taken from internet. Next slide please. Yeah, so many years ago people were studying artificial intelligence as a subject where expert systems used to be the main theme. So domain-specific knowledge was organized in knowledge bases, and some rules were built on top of them to take decisions or to support in decisions. So that was more like a programmed system. So how things would work were pre-programmed. And they had very limited success. The scope was limited to the size of the knowledge base and the rules that were built to retrieve knowledge. And later the emphasis changed from programmed algorithms to learning algorithms. So when you have data giving you the actual scenarios, the algorithms then would learn the relationships between the different inputs and the input variables, so which became a very different paradigm, because one did not have to pool a lot of knowledge base, a lot of these rules, etc. The systems could actually look at the intricacies of or the complexities of the relation between the data. For example, if it is recognition of a person, then what are the inputs, and the result will be the person is so and so or not so and so, etc. So the learning algorithms could exploit what are the different inputs, how they are related to the output, and so on. And then in this process, a lot of emphasis came on what are called features. So whenever we talk of machine learning, we have to take note of what are the attributes of the data that we are basing the learning on. Next slide please. So we have a lot of these examples, say database mining, where the data is coming from internet or from hospitals, biological research, engineering research. So what kind of things that we can learn that can be goal driven, and these learning algorithms can be built on top of it. Okay, and here it's very difficult to foresee everything and build the applications purely by manual control. So for instance, autonomous vehicles, recognizing handwritten text or spoken languages, vision, So there is so much diversity that one cannot have end-to-end closed solutions to solve the problems. So learning here helps in evolving the solutions. Next. Just an example. Next. Yeah, so just for history, what is the definition of machine learning? So the 1998 definition seems to be well accepted. Okay, so it's like to learn from experience E with respect to task T, and which is measured by some performance measure P. And as learning happens on the specific task T, and so based on the evaluation measure P, performance improves with experience E. So this seems to be it happens all the time, even for us also. As we gain experience, we tend to do some tasks more efficiently. So I can say that for myself, how I was when I started teaching, and after all these years, I am probably a slightly better teacher. So it's experience and performance measure and task. So these three together are into the definition of machine learning. Next slide, please. Basically, if you look at machine learning, you can say that it is used for two broad applications. One is classification, associating the data with some labels. So whether it is vision, whether it is language, or whether it is some other kind of thing, or it is estimating the values of continuous variables. So can we predict the load on say our power grid as battery driven electric cars are increasing in numbers, because we need recharge stations for the cars. So compared to the past, there will be more demand on the power grid in future as the fuel technology moves from the petrol and diesel to say the new technology where we have stored energy batteries. So if lakhs of cars are recharging the batteries every day, so we need that much more electric power. Okay, so can we make a prediction on that? And if we are importing more and more of these electric cars, what happens to the dollar exchange rate? So you can think of various kinds of problems where we are estimating the value of a continuous variable. So it's not saying that this is this object or that object, but what is the value of this if certain input conditions come together. That is the regression problem. Machine learning is very actively used for both. Next. So my talk is basically about classification, and so any general machine learning technique with classification as the goal, you can think of it as putting together a discriminant function. So there is some input data, capital X, and we have some discriminant functions. Okay, so one may be for each class. And so if given this data vector, one of the we need to determine certain parameters of the linear hyperplane so that we are able to assign the data to the corresponding classes. So how do we determine the parameters? For that we need the examples, right? So given the sample data and their corresponding classes, then we will be able to make a generalization and any new data element can be assigned to a class, right? This is what as teachers we always do. Some problems are solved in the class and students try to solve new questions in the exams. If the learning is satisfactory, in the exam the performance will be good. Next. Okay, we can skip the details because I think Sanjay will be covering them in more detail. Next. Yeah, you can see this how linear separability means how certain kind of problems can be handled and how certain cannot be handled. Next. So this is one situation where you can have an AND. So one side you have both ones and the other side both zeros are one of them zero. So this is situation of an AND. Next. Next. Yeah, this is like an OR situation. So, and after this comes the problem. Next. Next. Yeah, so you have a situation where a single linear discriminant is not able to solve the problem of exclusive OR. Okay, which, I mean, if you people have been into neural networks or machine learning already, you are very well familiar with it. A single partition cannot handle this exclusive OR situation. Right? All of you are well familiar. Next. Okay, so we can make a general statement about accurate or successful classification. One is how good and how much is the training data or examples, how many examples are we able to provide to the classifier, right? So if you have a set of the examples which adequately cover the full diversity of the input data, and you have sufficient number of examples to cover all the possibilities, then that is a factor which can help in accurate classification. The second is feature vectors. So what do we mean by feature vectors? Let's think of how a doctor makes a diagnosis. So when a patient visits the doctor and if a disease is suspected or if a disease is to be ruled out, then there will be various kinds of tests. So starting from simple measurement of body temperature, blood pressure, etc. Then you can have ECGs and blood chemistry. All these things together, they are the features which help in making the decision. So for example, high temperature may be possibility in 10 different diseases. So if you have only temperature, you will not be able to make a decision. Or low blood pressure, high blood pressure, or elevated sugar levels. So you have to put together many kinds of these inputs, these different kinds of data. Okay? So the richness of the data comes from how many different types of measurements do you have associated with each data element. That is a feature matrix. Now, coming from where I work with satellite images. So if I want to study the possibility of striking gold in a particular area, so I need the soil type, soil color maybe, the kind of vegetation that is grown there, the gravity data, because if there is heavy metal under the ground, the gravitational force may be high compared to nearby places. So you have equipment which can measure the gravitational pull, gravitational force. So they are called gravity surveys. Likewise, in some cases, the magnetic field variation can be there. Okay? So you have aeromagnetic surveys. And then, how is the radar pulse in the microwave region getting scattered back? How is the light energy getting absorbed or scattered in infrared region, visible region? So these are all kinds of input features for me. Okay? And then the learning algorithm. Third is this. Okay, you have very good data, large number of examples and very rich feature set. But then how good is the learning algorithm? Is it able to exploit the full power of the feature space and the training samples? For example, if a classifier just uses the mean vector of the data and nothing else, its capability is very limited, right? Or if it makes assumptions about linear separability of the classes and only on that premise it assigns classes. So it's like, again coming back to the medical application, suppose you have a doctor who doesn't know how to associate all the input data to come up with a decision. So the power of the learning algorithm, the rich set of features, the quantity and quality of training data, all of these together will ensure accurate classification. Okay? So machine learning today, the advances are focusing on the second and the third. In some situations, you don't know what features are required. Okay? And you also need more and more powerful learning algorithms for giving you very high accuracy of recognition, for example. This is where Google and Facebook and many of these companies are currently working. So today, for example, you take a parrot and name it Aishwarya Roy and then put it on your website and you search for Aishwarya Roy's pictures. So the parrot will also come. Right? So therefore, the fully successful face recognition, etc., it's happening, okay, but it still has some way to go. Okay, so today's machine learning algorithms look at how to choose the appropriate features for a particular task and how to learn the relationship between the input data and the classes, whatever be the complexity. Next, I'll quickly run through a few examples. So, for example, so this is one possibility. Okay. Next, this is also a possibility. Next, this is also a possibility. All of these are possibilities. You can have infinite number of these discriminants which separate with 100% accuracy these samples. So which one is the best? So if you want to choose one of them, you have to impose some kind of an optimality condition. Right? So in other words, you have to say that some discriminant is not so good compared to some other discriminant. So the support vector machine classifier, which is extremely widely used today, it defines what's called a margin. Means, okay, you have given me some samples. Based on that, I can build a discriminant and say that, okay, these are one class and the rest are the other class. But if I am likely to encounter samples which are different from these, but in the same class 1 and class 2, then will my discriminant be able to cater to them? Will I be providing a little margin? Suppose I say men height will be 5.7, 5 feet 7 inches onwards, and then ladies say 5 feet to 5 feet 5 inches. Suppose I make such a trivial assumption. What if some ladies are 5 feet 6 inches tall? Or if some men are shorter than 5 feet 7 inches? I should have a provision, a margin, right? Same way, suppose I am making some measurements using some sensors. Okay. So, from what I have measured, this is the situation. But I could not have measured everything possible. So there can be possibilities that this particular class may have a few samples where on this axis the values may be smaller. Right? Or if you take this one, their values may be, say, somewhat lower. Whatever be the situation, I should have as much margin as possible for accommodating data of this category to vary beyond these samples, and data of this category to vary beyond these samples, and yet be correctly recognized. Okay? So 5 feet 4 inches male should be recognized as male. Okay? If there is sufficient margin for the heights to vary. Okay, next slide. So if I evaluate this particular discriminant, I find that if this sample, okay, takes a slightly smaller value along this axis, it goes to the wrong class. Likewise, if this sample, okay, its value varies a little bit and comes on this side, it will be wrongly categorized. So the margin for variation is very, very small. So if I choose this as the discriminant, as the partition for separating the classes. Mind you, what are important? The important ones are only those which are close. Samples of this class and samples of this class which are close to each other, they are the more critical ones. Here there is no problem, and here there is no problem. Only which are close. So they determine where you can draw the partition. So in mathematics, support of a function is the area, is part of the subspace where the function is valid. Okay, so the support is a mathematical term here. Vectors, because in general the data elements are by default vectors. So these are support. Machine means a classifier. That is how the name support vector machine has come up. Next slide. So if I were to draw this discriminant, I can see that there is more margin for these data to change and yet remain in the correct class. Likewise, these samples also, they can change, they can vary further and yet remain in the correct class. I have greater margin. So obviously this should be more desirable compared to the previous one. Am I getting across to everybody? So this is the basic principle on which support vector machine works. That it builds into the formulation of the classifier itself a provision for accommodating further variability of the data within the class. So intra-class variability is better accommodated by this. Neural network doesn't know it. Neural network's task is just to separate the data correctly into their respective classes based on just the training samples. So it doesn't know how much the samples can vary further. Okay, so that's why you have generalization and all that which comes about. But the mathematical formulation itself, support vector machine builds this capability. Okay. So obviously now you have an optimization problem here, that is maximize the margin. How do you define the margin? Margin is basically the distance of the samples from the discriminant. So distance of a point to a line, plane, hyperplane, whatever, it's not very difficult to mathematically calculate. Right? So the smallest distance comes from the support vector. Right? Next slide. Next. Okay, so why maximize the margin? Next. So if you want to draw the partition at the correct location, we need to first estimate the margin wherever the discriminant is. How do you determine the margin? Next. Yeah. So from any point, this is the distance. Next. Next. So you want to find the smallest distance. Smallest distance comes from the support vector. Okay, so if you draw the discriminant, you have the support vector with respect to that discriminant. Now, you maximize the smallest distance. That is the problem that you have at hand. Next. Next. Yeah. So if you are given a discriminant with respect to the data elements, you can find the distance. Now you want to maximize this distance from the nearest sample. That is the problem of margin maximization. So this is the optimization problem. We have a maximization. Now are there any constraints? Whenever you are trying to maximize something, you have to have in mind that there will be certain constraints. Like if the government wants to beautify Mumbai, can they clear all the slums? There is a constraint that next subject to. So maximize this margin subject to the constraint condition that the samples that you already have in hand, which you know which belongs to class 1 and which belongs to class 2, that class assignment must not be disturbed. That is the constraint. Right? So you draw a discriminant in such a way that you get maximum margin with respect to the support vectors, and you also have to ensure that the samples of class 1 are on one side, samples of class 2 on the other side. That should not change. Okay? Next. So the full algorithm, probably someone will cover it. I only highlighted the problem. The full derivation optimization problem with duality, etc. It itself will take another hour. Next. Okay, you can skip this. Next. So one of the problems can be if there are noise samples, there is nothing you can do about either this sample, which is in the middle of the white circles, or this sample, which is in the middle of the dark circles. You cannot have a discriminant drawn which can handle this. So if you have outliers, all you have to do is accept it that some data elements will be misclassified, and for the majority of the remaining samples, you should be able to correctly classify. So this is the outlier problem. So support vector machine calls it a slack. So you have to specify a slack parameter which determines how much error can be accepted right in the beginning. So if you have very noisy data, the slack variable value will be high, and if you have a really good quality noise-free data, the slack can be very, very small. Next. Yeah, this is the other situation. We talked so far about linearly separable data. You are able to draw a line or plane or something. What if you cannot do it? So for this, one takes help of some great work done by a late Stanford University professor by the name of Thomas Cowell. So what he said is, the probability of separating data linearly increases if the data is non-linearly transformed to a higher dimensional space. Okay? Because linear scaling will not change the order. So non-linear transformation to a higher dimensional space will take care of it. Next. So a second order polynomial based transformation gives you this kind of data. Next, which can be easily separated. Again, it's linear. Problem solved by non-linear transformation. Okay. So these are the major things that you have in support vector machine, which is bread and butter machine learning algorithm. So first, margin. Second, tolerance to noise. Third, nonlinear transformation to take care of linearly non-separable data. Okay. So there is one more problem that I have not addressed. What if you have more than 2 classes? Suppose I have 10 classes. If you are looking at, for example, this room, and and I want to take an image of this room and want to classify. So there are chairs, there is flooring, there are people, there are lights, ceiling, okay, all the paneled walls. There is so much to classify. Not just two classes, there are many classes. So in that case, support vector machine gives you a provision that you take one class out and bunch all the others into the second class. So once one class is out, take the rest, again from that pull out one class and then bunch the remaining 8. So 1 and 9 you separate, so 1 is out. Now from the 9, 2 and 8, then 3 and 7, 4 and 6, like that. If you have 10 classes, 9 support vector machines will take care of it. Or even better, you separate every pair of classes. Separate 1 and 3, 1 and 4, 1 and 5. So you have, if you have n classes, n C2 support vector machines will separate every class from every other class. In fact, this works much better. Even though the number of machines, support vector machines will be high, but it will be much more reliable. Every class is separated from every other class. So these are called 1 versus 1 and 1 versus rest approaches to SPM. How many of you have actively used SPM already? Anyone? Not yet. Okay. Next. Yeah, since I use satellite images, I have only this kind of examples. So this is agricultural fields where there is no crop at that moment, dry river bed, some roads. This is a kind of a small village. This is the kind of image I have. Next. And this is the classification. Next. By the way, go back. There is a very popular library for support vector machines, so you don't have to program everything by yourself. libsvm, if you are used to programming with MATLAB, for example, the library is available. This works with C language, with MATLAB, etc. So you can very rapidly build a support vector machine classifier with this library. Next. Yeah, this is another example. High resolution satellite image of a small part of Mumbai outside IIT. Next. And these are the classes. Next. So the other popular classifier in the regular machine learning is the neural network. Next. Why study neural networks? Obviously, why is it important? In fact, neural network research started before support vector machines. So it's the word neural refers to the neurons in the human brain. So neural networks are also used for modeling the structure of brain and the behavior. And in fact, today's computational models of neural networks are based on the hypothesized structure of the brain. Next. And they are also used for solving difficult engineering problems. Next. In fact, the Visa credit card company had deployed neural networks first in the major investment for detecting fraudulent card transactions. They made the neural networks popular in the industry. Next. This is the biological neuron structure. You have the dendrites, which bring the inputs, and then you have something like a potentiometer, which is called the synapse, which changes the gain, effectively the gain of the input signal. And then there is a branch which takes the output, and at the end of it you have a lot of these dendrites, so that the output gets connected to many other neurons. So this particular neuron receives inputs from a large number of neurons, and its output in turn is connected to many other neurons. Okay, so in our brain you have billions of neurons, and each neuron is supposed to be connected to thousands of other neurons. So you can look at a massive parallel processing. But each neuron is very primitive in its capability. That's why, say 19 into 18, you take time to calculate. But what you see in front of you, you can recognize in fraction of a second. So where parallelism is no use, our brain will be very slow. It's no match for the cheapest calculator in the world. But when it comes to tasks like speech recognition or face recognition or any such things, it will be a challenge for the most powerful supercomputers to match. Next. This is a comparison. Next. And this is a computational equivalent. Next. Yeah. So effectively, this is what happens in a mathematical representation. There are inputs. Each input is scaled up or down by a weight factor, and there is a bias. So when the inputs all get aggregated, that is non-linearly transformed, and that goes out to connect to other neurons. So this is the representation. Next. So what kind of nonlinear transformations happen? The models are like sigmoid or the radial basis function. So for the mathematical tractability of the algorithms for training the neural networks, this kind of functions are chosen which have any number of derivatives. Okay, smoothly varying functions. Next. So this is a typical neural network which can handle any nonlinear classification problem. So the user supplies inputs which can be observed at one extreme, and the user can observe the outputs at the other extreme. And in between, you have all the computations happening which the practical end user is not interested in. Okay. So for terminology sake, they are called hidden layers of neurons. The input what I am feeding to the network I can observe, and what the network is throwing out I can see at the output. So in between, what happens? I mean, if I am just a simple end user, I don't care. If I am a programmer, if I am a neural network researcher, I should. What are the implications of how many layers in between, how many elements in each layer, all that I should know if I am a neural net researcher. Okay. Next. So again, the algorithm for training such a network has become pretty popular when the feed forward topology is followed. Next. So the partial derivative based chain rule of backpropagation training. So the signals move from input layer to output layer, and from the training data one can observe the difference between the desired response and the computed response. So the error is used to adjust the network configuration, not the elements, numbers, but the connection strengths. Okay, so the connection strengths are adjusted. So based on the error observed at the output. Again, I am skipping the details because I expect detailed lectures will be there. Next. Yeah, so in the forward pass, input to output, signals will be flowing left to right. Next. And in the backward pass, the errors are propagated to adjust the connection weights between layers of neurons. Next. Yeah, so what are the typical problems with this? Next. Yeah. So the error may come down rapidly and then it may stagnate over some time and then it may fall again and then it may stagnate again. This is the kind of behavior that one observes if one is actually working on neural net applications. Next. And one can also have a very poor solution when using a neural net because next, the network may stop at a point where the error has not reached a really low value. The error in the accuracy of classification has not reached a sufficiently low point, but the network stops at that point. Okay. So if you can think of the error surface as a hilly terrain with peaks and valleys, if you want to reach the lowest point in that, sometimes you may not succeed based on where you start. Okay. So there are ways to deal with it. Sometimes one uses genetic algorithm to initialize the network in such a way that you have a very high chance of reaching the lowest error. Next. Yeah, so what are the configuration issues? There are guidelines. So if the network is not able to learn well from the training samples, you have to adjust certain parameters like increase more elements in the hidden stage, etc. Next. And if it's taking too long to converge, maybe the network should be restarted basically. See, it's an iterative process, so whenever you have iterations, you need a starting point. So when you have a starting point, which starting point takes you to the convergence faster, that is an issue, and usually we don't know where to start. So what we do is we take help of random number generators that programming languages provide us. And so we initialize randomly the parameters, and then we hope that in course of time you reach the optimum values. But for these days, you have the help of global optimization methods like genetic algorithms, simulated annealing, etc., which can initialize the network in a much better way so that you are guaranteed to reach a sufficiently low point. Results that we have. Next. if we can look at what is inside a pixel, and we also estimate the image itself as if it is acquired with a higher resolution. So suppose you have a camera, 10 megapixel camera, you get an image. Now can you estimate what it would be if it were captured with a 20 megapixel camera? That's a super resolution problem. Okay? So this is what we attempted. If the original image is captured at say pixel size of say 10 meters by 10 meters on the ground. Now can I estimate what it would be if the image is acquired at 5 meters by 5 meters pixel or 2.5 meters by 2.5 meters pixel? So that is a super resolution problem. So again, deep learning is very heavily used for this. Next. Mohan. So some CNN model was built, and so from the input image we simulated a coarser resolution version of it and then estimated the higher resolution one, which we could now compare with the original. Of course, there is a brightness difference, but that can be adjusted. It's not really a problem. Okay, so this is where things stand, and the next one on top of deep learning is called the convolutional neural net. On top of it, something called capsule net has been recently introduced in 2017. So people are now moving on to capsule net because the examples shown were extremely interesting. Suppose I write one number and overwrite on it another number. It will be difficult even for humans to separate, decipher that. But the capsule net is shown to separate. Okay, these are the two numbers which are overwritten. You will be able to give that kind of performance. Okay. So all the best and have a good time in the course.